Hi, we are live from ZCon 2. I'm Deirdre Connolly. Sean, can you introduce yourself?
Yeah, I'm Sean Bowe from the Electric Coin Company.
And Dara.
I'm Dara Hopwood, also from the Electric Coin Company.
And we're here today to talk about Halo2 and Orchard, the newest Sapling shielded pool, the newest shielded pool for Zcash that came about because Halo and Halo2 incited it into being. So to talk about Halo and Halo2, Sean's going to tell us about recursive proofs.
Yeah, to sort of understand where, why Halo is a thing, why do we need it, what does it have to do with Orchard? It's useful to sort of revisit what recursive proofs are, and they're the sort of thing that we actually need, and they're the important part of our roadmap going forward when it comes to scalability. So proofs of knowledge are cryptographic tools that can be used to show that you performed a computation. And we use these in Zcash. We use zero knowledge proofs or arguments of knowledge. We use these SNARKs to create shielded transactions. And you don't necessarily need the zero knowledge part. You can do a lot of really awesome stuff with just the proofs of knowledge themselves, including like compressing computations and proving that you performed computations on behalf of someone else. So one kind of interesting question is, what happens if the computation that you're checking that someone else performed is itself verifying a proof of knowledge? And this is what we refer to as proof composition. So the next question you might ask is, what if the inner proofs computation that you're checking when you're doing this composition step is the same as the outer proofs? It's just a different instance of the same computation, different inputs. This is what's known as recursive proof composition, and we can use this to compress basically unlimited amounts of data into a single proof, which is really awesome. And it's really helpful in scalability because we can compress checking computations like, for example, is this block correct? Are these blocks correct? Are these transactions correct together? And it's just one of many different useful tools that we can use to scale Zcash. So on the next slide, as a background, before our team discovered Halo, recursive proofs kind of sucked in practice. They kind of sucked. They were on large elliptic curves, and they were kind of inefficient, and they required trusted setups. And all inefficiency we've kind of been addressing over the years, for example, with Sapling and stuff. But requiring trusted setups is one of those things that we sort of have needed for the most part over the years because SNARKs just weren't efficient enough. So when we discovered Halo, we finally discovered not only a way to do recursive proof composition without trusted, really efficiently, but also it didn't require a trusted setup. And that sort of solves all of our issues when it comes to the proving systems, which is awesome. So like I said, recursive proofs address scalability issues, and we can use them to address scalability issues. After we posted Halo, there's this flurry of new papers, not only building on top of Halo. I guess Halo set off sort of this new lineage of recursive proofs that were more and more efficient, and new ideas are coming out every other month at this point. Also, in parallel, the crypto community has sort of been building new SNARK constructions, and we can sort of cross-pollinate ideas from both of them. In particular, new ideas from SNARK such as Plonk. So what we've been trying to do over the last year or so is combine some of these new ideas and some ideas and optimizations of our own together with the original Halo concept into this suite of utilities that will allow us to do recursive proofs really efficiently and use them in Zcash if we can. So I can't explain the concept entirely in too much detail. It's too technical for this short of a talk. But essentially, when you look at Halo, what we understood was happening when we created Halo is we came up with a way to make the recursive proof composition work using SNARKs that don't require a trusted setup. Viewed in another lens, the academic community has sort of started to look at what we're doing, and what they've interpreted it and formalized it as is this general concept of an accumulation scheme. The idea is that instead of recursively checking the proofs, look at it like that, instead we're sort of adding proofs to accumulators. And those proofs are checking that the previous state of the accumulator is correct. And so as long as you check the latest proof and the latest accumulator, then you know that by induction, you know that all the proofs that preceded it were correct. And you can do this in sort of a tree. What you see in this slide resembles sort of incrementally verifiable computation, but you can do proof carrying data, which is just this generalization of it that involves sort of trees of computations. The other important thing to note is that, like recursive proofs prior to Halo, we use elliptic curves that form a cycle with each other, so that it's efficient to prove things about proofs on the other circuit, or on the other curve, and then you sort of bounce between the two elliptic curves. And so that's why we actually end up having to have a cycle of curves, which I'll mention in this next slide. So what's Halo2? Halo2 is a zk-SNARK, recursive zk-SNARK proving system that we're building on top of what are called the pasta curves. Pallas and Vesta are their individual names. And it takes what some practitioners call the ultra-Planck arithmetization from Planck and sort of integrates it into Halo. And this supports, unlike rank 1 constraint systems, which are what SNARKs used to use very commonly before 2019 or so, these sort of ultra-Planck and related arithmetizations and things like lookup arguments and all this other stuff really allow you to build very efficient proofs for complicated protocols, much like Zcash. Zcash is shielded technology. So yeah, so the proofs for Halo2 proofs end up getting a little bigger than Grok 16, but they're actually not that much slower to verify. So they and together with these optimizations we've been doing, they just barely fit within the sort of efficiency profile that is sufficient for use for integrating it into Zcash. So on the next slide, if you want to learn more about Halo, there's a couple other talks that go into more technical detail. There's one I did for ZK Study Club, I think, and there's another that Nick Spooner from UC Berkeley did at TCC or whatever that conference is called. Cool. Next slide. I think I'll hand this off to Deirdre.
Yeah, so now that we have this cool new recursive proof system that eschews the need for a trusted setup, why couldn't we just slot that into what we have in Zcash already, the latest and greatest shielded protocol, which is Sapling? Well, the first thing that falls out of a new proof system like this is the curves that Sean just mentioned. We have the curve that we use to create commitments, like no commitments and value commitments. And we have the curves that we're using inside the circuit. As soon as you change those curves, you got to change the commitments. They're represented by different group elements, elliptic curve points, in the broader protocol. So in Sapling, we use the jub curve for things like for the spend dot signatures, for the binding signatures, for the note commitments, for value commitments. All of that is using the jub curve. With these new curves, we need to change all of those pieces of the shielded protocol. And once you start changing this bit and that bit and the other bit, they all work together. So new curves means we need to change a bunch of pieces of the whole shielded protocol. One nice thing though about the new pasta curves is, since we don't need to use pairings anymore, we don't need pairing friendly curves. Therefore, our curves can be smaller because we can use to support pairings with a pairing friendly curve. Those curves generally need to be bigger and have bigger fields to be cryptographically secure. So we don't need those anymore. That's one plus about Orchard and the pasta curves, they are smaller curves. So we get the cryptographic security, but they're smaller and they are prime order. And that makes a lot of how we model the cryptography and do proofs and things much nicer. And it's just simpler to reason about. Fewer edge cases. This also gives us an opportunity to change how we hash values into the group, literally called hash to curve. Previously for Sapling, it was not a quote total over all of the domain inputs to the hash. Basically, for the new thing for Orchard, we have a valid solution for all the possible inputs when we are hashing into the Pallas curve, which is very nice, and it's constant time. All these little things that were opportunities to improve for both the security of the protocol, proving the security of the protocol, reasoning about the security of the cryptography we're putting together in Orchard, just are much nicer when you have these sort of building blocks. One of the other well, not a downside, but sort of, you have to change how you're doing your verification of proofs of the consensus rules. When you have a proof system like Halo2 that's different enough from Groth 16, you have to make optimizations. Otherwise, it just would be a little too slow. So that necessitated further changes. Halo2 allows for efficient lookup arguments, which led to the design of the new hash called Sinsemia. It's a collision-resistant hash that is more efficient with those lookups. Sinsemia is very similar in spirit to the Pedersen hashes that are used in Sapling. It uses group elements inside it, so some of these pasta curves to construct that, but it's much more efficient when you're using it inside the circuit. And then we wanted to remove hashes that are expensive in a circuit, such as Blake 2S. So we had to change those as well. And then the last bit here is when instead of having spend statements and output statements that you can have multiple of those in a single transaction, it's been changed into an action statement and action transfer, which is doing all of those pieces together. If you have one of those, it leaks less metadata about ins and outs and how many of them in spends and outputs. It's just one final value that you might find information about instead of spends and outputs. So Orchard turns out to be very similar to Sapling, except where it's not. Take all the good bits that we have in Sapling, drop some of the less good ones, such as the more expensive hashes, less good hash to curve, that sort of stuff. And then you add in all the optimizations that you can get out of Halo2 and that you need to make the most out of Halo2 inside the Zcash protocol. So what's the same? Still support viewing keys, outgoing, incoming, full viewing keys. Still support efficient signing on hardware wallets. Instead of using the red jub signature for spend auth and binding signatures, it's red Pallas. It's still the red DSA construction that allows for re-randomizable keys, but instead of jub, which was a cofactor curve, we use Pallas, which is a prime order curve. It's another nice thing that having a prime order curve like Pallas gives us is just one less thing to worry about, in this case, cofactors. And we have equations now to do prime order arithmetic on curves such as short Weierstrass curves. That's perfectly efficient for our needs. Support for diversified addresses. Also, if you would like to learn a little bit more about re-randomization and diversified addresses, the Frost talk later today will touch on a little bit of this. Frost supports all of these re-randomizable issues for Sapling and Orchard. The balance checking is the same. We still take all of the value commitments that are published on the blockchain, and we do our homomorphic operations to get the verification key out of the balance to check the balance. Node encryption is the same algorithms all the way down for how we do derivation and encryption of notes and note metadata on the chain. And then the node commitment tree is a binary tree of the same height. It's literally copy and paste the same no commitment tree between Sapling and Orchard. You just swap out one kind of hash for the different internal nodes of the tree with the new one. It's pretty nice from an implementation perspective. So how is it different? A little bit, as I mentioned before, tweaks made to the protocol level to optimize for Halo2 and for the ultra-Planck arithmetization inside that you use to define the circuit. As I mentioned, instead of spends and outputs, it's just one thing, it's an action. You can have the notes that you're spending and the notes that you're outputting from one spend transfer, action transfer. We're computing nullifiers differently now. As I mentioned, we wanted to drop Blake 2s. By doing this computation in a different way, we're able to drop Blake 2s, but we're still very happy about how these nullifiers are derived. And I think Dara will go into a little more detail about that. One biggie that we'll talk about later, unified addresses. One of the previous talks talked about the usability around unified addresses in the wallet and the SDK. If we had followed the traditional path of introducing yet another shielded address type for Orchard, we would have had 4. So instead of introducing a 4th, we introduced unified addresses that should be a way to have one address for all of your possible pools of ZEC. As well, what's different, a full viewing key and your spend authorization key is sufficient in order to make your proof and to make a Zcash shielded transaction. There is no nullifier deriving key anymore. And no commitments are unique in a valid chain. This helps.
Just a correction. NSK isn't the nullifier deriving key. It's the proof. It's the specific key that you need to make a proof in Sapling.
Oh, okay, never mind.
NK is the nullifier deriving key.
That's where I got confused. And no commitments are valid unique in a valid chain. This helps an implementer of a node very much. You can dedupe node commitments in your data store, and it helps you out a bit. Okay, Dara, can you talk about the circuit?
Yes. So Deirdre talked a little bit about removing the heavyweight hash functions. Blake 2s is not normally considered heavyweight outside a circuit, but in a circuit, it takes 26,000 odd constraints, R1CS constraints, I think.
21,000.
Yeah. So a Sinsemia hash requires only, if it's 510 bits of input, that would be about 52 rows of a Planck circuit. So obviously there's a big difference there. So the Pedersen hashes in Sapling, they were something like 1,380 R1CS constraints. So you can see the Blake 2s is much more expensive than either of those. So we make use of custom gates and lookups. A lookup, basically you can have a table and the number of entries in the table is limited only by the circuit size. So we use a 2 to the 10 entry table, and we use that to look up bases for use in Sinsemia. The total circuit size of Orchard is well, it's less than 2048, which is 2 to the 11 rows and 10 columns. So that comparing performance between a Planck circuit and an R1CS circuit is actually quite difficult. They're not really comparable, but this is very good. Yeah, and if you, the concrete performance, which we don't have proving numbers yet, but we do have circuit verification numbers, and it's only 20 milliseconds, even single threaded, and even without batching. Yeah, so if we can compare this with the Sapling spend circuits, that was 96,500 constraints. And yeah, so you can see even with the incomparable number of constraints, it's quite small. And in particular, when we add recursion, the Orchard circuit is going to fit below the Halo2 recursion threshold. So a recursive proof system has a minimum size of a circuit that it needs in order to support recursion, and the size of the Orchard circuit is below that. And even if we add CSAs, then it's still going to fit within 2 to the 11 rows. There's a step change in the proving cost when you go above a power of 2. That's the same as Grot 16. Okay. Yep. Next slide. So this is a kind of visualization of the circuit layout. There's kind of an analogy between a Planck circuit and an integrated circuit in hardware, say. So if you look at the layout of the left-hand side of this, the sort of khaki green one, that is showing the advice columns. So that's the ones that contribute most to proving cost. And you can see that this has been very tightly packed. There's some inefficiency at the bottom here. This pink area is sort of where we have some inefficiency in the layout, but that's just because we need to improve the layout algorithm a little bit more. The total size of this box, see the white part at the bottom, that white part ends at 2 to the 11, so we've got plenty of room. And this this part on the right is the fixed columns. So they basically determine sort of what kind of functions you're using at each point at each row in the circuit. And this see the box in the middle, which is 3 columns wide and about half the circuit high. That's the lookup table for Sincere. Okay, next. So let's talk about Sincere now. So for Sapling, we introduced the Bow-Hopwood Pedersen hashes, and they were sort of a big improvement on using, well, at Sprout, we used SHA-256 for the Merkle tree. So that by itself, I think, improved the performance of Sapling by about 10 times. And the advantage of using Pedersen-based hashes is that we're already relying on the hardness of the discrete log problem. So a Pedersen hash has security that can be reduced to the discrete log problem. So you're not relying on any extra assumption for collision resistance of the hash. And Sincere retains that property. You can actually prove that it's as secure as a Pedersen hash. And we also use it for some of the commitments that we need in the circuit. So the reason this is more efficient than the Pedersen hashes is that we can process 10 bits at once using a lookup rather than 3 bits. And the 10 bits comes from that, the size of that table that you saw. It's 2 to the 10 entries. We actually can do 2 Sincere hashes in parallel on each row. So it's as if we're processing 20 bits at once. And the security proof that reduces Sincere to a Pedersen hash, it's basically, you can think of it as a Pedersen hash on its side. And I have an explanation of that in more detail. There's my ZK study club on Halo, and there's also a ZK Soul presentation, and we can add those links to the Discord. Okay. Oh, another thing is that we go back to that slide. So it's more efficient to use incomplete curve additions. So because we're using a short Weierstrass curve, the simplest equations for addition on the curve don't necessarily work for all points, but we can prove that in those exceptional cases, we will be able to find a discrete logarithm, and therefore the exceptional cases must happen only with negligible probability. Okay, next. Okay, so what security properties do we want from a decentralized payment system? We want balance. Do transactions preserve the total amount of money? You can actually always send money to a key that no one knows, so you can destroy money. But the point here is, can you create it out of nothing? Need spend authentication, so I shouldn't be able to spend Sean's money, for example, without knowing his private keys. Then there are the privacy properties like, can I gain information, for example, from the note ciphertexts that are sent on the blockchain? Or can I derive information from note commitments or nullifiers? We split this into several properties just in order to sort of get stronger properties when the adversary doesn't know certain information. And then there's Faerie Gold resistance. Can I cause notes to be accepted that may be unspendable? So that the attack model here is, say, I'm sending Deirdre 2 notes, and she verifies that they're valid notes, but she ends up only being able to spend one of them. So I could use that as part of some, I don't know, social engineering attack or refund scam or something like that. Okay, next. So let's look at how the security assumptions that we need for each of these properties compare from Sapling to Orchard. So basically all of the instances of Jub become Pallas because we just changed the curve. For balance, we only need to, keep on that slide. For balance, we only need to assume discrete hardness of discrete log. For spend authentication, we need the red DSA signature scheme to be unforgeable, and that again depends on discrete log. For note privacy, there are 2 properties we're interested in. One is the out of band property. So that's saying, suppose that I was giving you a note by some assumed secure channel. I'm not sending it normally on the blockchain. What information does the blockchain leak about that would allow to break the privacy of spends using that note? And you can actually prove that it's perfect for Sapling, so that no cryptographic assumptions are needed, and near perfect, it's statistical security for Orchard. And the statistical distance from perfect is very, very small. When you send a note on the blockchain, obviously you're also dependent on the security of the note encryption. So that's this hashdh assumption, and Blake2b here is the key derivation function. So spend on linkability, this is basically, suppose that I send you a note and you spend it. Can I, even as the sender, detect when you spend it from the blockchain? So can I link the nullifier that you publish with the commitment that was posted in the transaction? And in Sapling, this was dependent on Blake2s as a PRF, as a pseudo-random function. So for Orchard, we replace Blake2s with Poseidon, which is a circuit-efficient hash function, but we don't want to rely entirely on the security of Poseidon as a PRF, because it's quite a new hash function. So we use this construction that is secure if either Poseidon is a secure PRF, or assuming this decisional Diffie-Hellman assumption on Pallas. And there's a caveat there, which I don't need to go into. We also need to make a very weak assumption on Poseidon, even in that case. So the reason here, the reason for doing it this way and introducing Poseidon is, even if you could break discrete log, you are able to send notes out of band, or if the adversary doesn't know the destination address, then you would still have some security. And that's similar to what was called the, I think they called it everlasting security in the Zcash paper originally. And then Faerie Gold resistance, again, that's only dependent on discrete log. Okay, next. So let's actually informally give the security argument for balance preservation. I'm going into a lot of detail here, so I hope people are following along. So for balance preservation, you need there to be only one nullifier for a given note commitment. Because if you could have more than one nullifier, then a double spend wouldn't be detected. So we have this note commitment that binds these fields of the note. And what that means is that given a commitment, we know that there's only one possible tuple of these fields that will have that commitment. So this is exactly the same as in Sapling. So in Sapling, this also depends on the position of the note in the commitment tree. For Orchard, we'll see that it doesn't depend on that. And then, so we check that we check consistency of the address, which is this GD and PKD, with the incoming viewing key. And the property we need here is that there's only one incoming viewing key for a given address. So we've started with the note commitment, and now we know that there's only one IVK that can correspond to that note commitment. And then the IVK is derived from the full viewing key, AK and NK. And this is a collision resistant hash. So we know that there's only one AK and NK for this commitment. And then we derive the nullifier deterministically using this NK. There's only one of these possible, and rho, again, only one of these possible. So we know that there's only one nullifier for a given note. And this is for Sapling. So next slide. So there's just a few minor changes here. First of all, we're not depending on the position in the note commitment tree. Second change is that we have this extra blinding factor psi. Again, rho is unique to the note. So the next part of the argument is the same. We only have one IVK for a given address, and therefore for a given commitment. Here, instead of a collision resistant hash, we're using a commitment scheme, but that's also binding, so that's fine. The reason for changing this is that now we don't have to use Blake2S here. We can use Synsomere to construct a commitment scheme. And then here, to get the nullifier, we're adding this, we're still using the PRF. So if the PRF is secure, then that provides our unlinkability. We're adding this blinding factor, and that means that we don't have to depend on the PRF for privacy. Then we're basically adding the we're multiplying that by the base point G, adding a commitment. So the thing that makes the security property that we're depending on here is that all this is deterministic and only depends on things we've proven there's only one of the commitment. So we know that there's only one NF, only one nullifier that can happen here. I'm slightly losing my voice here, but that's fine. Next slide. Okay, cool. So we've done balance preservation. Next. And now let's do privacy. Yes, okay. So the places where we can leak information are note ciphertexts, note commitments, and nullifiers. Note ciphertexts, as we said before, are done in exactly the same way as in Sapling. And char-20 is a well-respected stream cipher. Poly 1305 is message authentication code. Those are all very widely used. They're used in TLS as well. So that's fine. For the note commitments, they're perfectly blinded. So they information theoretically, they don't reveal any information about the input. And for this nullifier, remember we're adding this random blinding factor chosen by the sender. And that basically makes this random, even if there were a weakness in Poseidon. So you can analyze this for two cases. You can assume that Poseidon's broken, in which case this scalar is still random. And so this multiplied by G is a random group element. So NF is a random X coordinate of Pallas. And then if you assume that discrete log is broken, then the PRF still saves you basically. So yeah, either way, the nullifier looks random. So the last thing that we need to do, we're nearly done, is a Faerie Gold attack. So thanks, Zuko, for coming up with the name Faerie Gold. That's where fairies give you some money and it turns to leaves in the morning. So this attack can happen if two notes have the same nullifier. And the reason this doesn't happen is that we're adding this note commitment here. The base G is independent of the bases used in the note commitment. And because of the properties of the Pallas hash, it's collision resistant, and that proves that you can't have two nullifiers. Oh, it's infeasible to find two nullifiers for the same node. Okay, that's it.
Thank you.
And I'll hand over to Deirdre.
Awesome. Now that we have a new circuit, a new proof, new curves, new commitments, new nullifiers, we've got a whole bunch of new stuff. This results in the new orchard key derivation tree. Kind of like in Sapling, you start with your root spending key, you derive your spend authorization key, you define all of the pieces of your full viewing key. From your full viewing key, you can derive your incoming viewing key, your outgoing viewing key, your diversifier key, and from the diversifier key, you can derive your diversified transmission key, and the diversifier that you generate plus your transmission key is your address. So if we had just done this like we had done for each previous shielded pool, we would have a new Z adder to juggle. And that would bring us up to count them four addresses that are technically viable on the Zcash blockchain, including transparent Sprout, which is on its way out, but Sapling and Orchard are definitely not on their way out. So it was getting hard from a user's perspective to be like, well, you know, which one, like have a keychain of your ZEC addresses about which one you want to hand out to give to people. And in our minds, we kind of think of, well, you know, ideally you would be like, oh, if you support Orchard, send money to my Orchard address. But if you don't support Orchard, maybe send to Sapling. And if you don't support any of them, like send it to my transparent one. Like, and we don't, and as of, I think, Canopy, you cannot send money to a shielded Sprout address. You can only take money out of a shielded Sprout address. So a design sprint at the ECC was dealing with this idea coming out of Orchard and resulted in this idea called unified addresses. And the idea is that you basically take that sort of, you know, priority arrangement of all the possible addresses that you, a user, would have for your Zcash wallet, or the ones that you have for yourself anyway, and just smush them together and then represent them. You can just give one thing to someone and say, send money here. And if they have an interoperable, compatible version of a Zcash wallet that would implement this zip 316, they would be able to parse that new unified address and figure out if you support Orchard, we'll send to Orchard. If you don't support Orchard, we'll send to Sapling. If you don't support Sapling, we'll send to Transparent. Or you could just have a unified address that is just Orchard or just Transparent, just Sapling, but does not support just Transparent. You have to have at least one shielded address as part of your unified address, because we think privacy is important and we want to encourage it. So one of the things that you run into when the naive approach about how to build something like this is to literally like take your T adder and your Sapling adder and your Orchard adder and literally concatenate them together, and just be like, sure, just split them up where you expect them to be lengthwise and then parse them out, right? Well, that doesn't quite work because you can have malleability attacks. You can it doesn't work. There are certain attacks where if you ever scanned your long address string and wanted to double check that this is the right one, like you might scan the beginning and you might scan the end, but are you really checking every single character in that whole, I don't know, 32 byte address string? Maybe not. So to avoid possible attacks that would leverage that very human thing, instead of just concatenating all these addresses together, we came up with a Feistel network, a 4-round Feistel network called F4 Jumble, which literally takes in all of the addresses and jumbles them up as part of encoding into a unified address, so that it'll always come out with a the encoded address in a secure manner. And then that resulting byte string is encoded with BEC32M, similar to how Sapling it was originally encoded with BEC32 and then supported BEC32M. Yeah, so that we have some time for questions. Orchard.
Another minor correction. Sapling addresses are still BEC32, and they're still going to be that after NU5.
Oh, I was confused because our libraries all upgraded with support for 32M, and then we had to be like, no, we're not using that yet. Thank you. Cool. So all of this stuff is part of the slate of zips that are scheduled to activate with Network Upgrade 5. Network Upgrade 5, and these are not all the things that are scheduled for Network Upgrade 5. There are some other items that are related to Orchard, such as making sure, so non-malleable transaction IDs are slated for NU5, and downstream of non-malleable transaction IDs, we have to support the network messages and the inv types for inv messages and get data messages to support the new non-malleable transaction ID with the correct authentication tag. And then other things like canonical point encodings for all jub points in Sapling. I think that might be everything in NU5 currently, knock wood. All of this is
That's everything.
Yeah, yes. Everything is scheduled currently to activate on testnet in July of this year. And then plan is to have mainnet activate in October of this year. We have audits ongoing of the spec and all of the zips that are going into NU5 and implementation audits that I think are just about to start as we head for testnet for Zcash. ZBRD is planning to have all of this supported for full validation for testnet, thereabouts, and for mainnet. We do not have a wallet yet, so we have a little bit less work to do than Zcash for things to support. But yes, Orchard's coming. Halo2 is coming, and we, knock wood, we'll get there very, very soon. Thank you all. I think we have some questions in the chat. One from earlier, can you please describe the Sinsemia hash? And Dara, maybe you could talk a little bit more detail.
Yes, so I have, I did a presentation which was partly about that to the ZK Soul group. So I can maybe find those slides and share them. Yeah. Can I take over the screen share?
Yeah, do I need to stop?
I think you do, yes.
All right, stopping.
Okay. Can you still hear me?
Yes.
I think my Zoom is maybe frozen. Oh, no, it's working. So I can do this. Well, I guess this will. Yep. How's that? Can you see?
Yes.
Okay, so let me find where the description of Sinsemia is. It's about. No, it's after this point. This goes into a lot of detail. Okay, right. So the basic idea here, this is the algorithm. So you take your message and you have you have a table of 2 to the k independent group elements. And you have 1 extra group element. So let's say that k is 10, which it is for the Orchard circuit. So we split the message into groups of 10 bits. So each of these is a 10-bit digit, and we use that to index into this array of generators. So that's what this is doing, PMI. And then we have a double and add algorithm. So we start with this fixed base point, and then for each group of the message, we double the accumulator, and we add the result of the lookup. And in practice, this is an incomplete addition. And then we just return the result. So why is this secure? It turns out to be secure to take the x coordinate of the resulting point. So we use that to improve efficiency. Okay. Why is this secure? Let's look at the what we multiply each base by. So these are the message words, 264251. So in the first round, we're multiplying by, sorry, we're adding P2. Then in the second round, we're adding P6. In the third round, we're adding P4, and so on. And each time we're multiplying, we're doubling the accumulator. So what we end up with is, if we look at these columns, then we end up multiplying the 0th base by 0, 0, 0, 0, 0, 1, the 1th base by 0, the 2th base by 1, 0, 0, 1, 0, 0, and so on. And so we basically have there's a one-to-one mapping from the message to this matrix. And then we just view it as a Petersen hash. And there's a one-to-one mapping into the input of the Petersen hash. And that gives us our collision resistance property. Cool. And this goes into a little bit more detail about how we optimize it and how we do the lookups. But we don't need to go into that here. I will just drop the link for this into the Discord. How do I stop screen sharing? There we go.
Cool.
Cool. Another question came in. What was your most challenging part while building Halo 2? In regards to either designing it or implementing it. So certainly implementing it is probably much harder than designing it. I mean, we've already done all the design and clever work when we came up with Halo, and just snatching some of the ideas from Plonk and putting them into Halo is really straightforward. I'd say maybe design-wise, making sure that we have a robust argument for zero knowledge was probably the most challenging part of design, but definitely implementation work, which in some ways is difficult to discern from design, was the most challenging, especially just really all the optimizations that went to Orchard in particular, not just Halo 2, but Orchard, required us to build some really flexible tooling and come up with some really clever tricks. So those are probably the most challenging thing from my perspective anyway.
I would say that the design of the nullifier derivation was also quite complicated. Getting all of those security properties simultaneously that I mentioned in my talk against all of the possible attackers who know different subsets of things is quite tricky. Yeah, but I'm happy with how that turned out.
I think we have time for one more. What did you replace Blake 2S with inside the circuit, since it seems Synsomia is only collision resistant?
I can answer that. Sorry, I had to mute myself to cough. So partly the commitment scheme. So we noticed that the, or I think actually in Myers noticed that the, we didn't need a collision resistant hash to derive IVK in the circuit. So even just in Sapling, we could replace that with a commitment scheme. And commitment schemes can be constructed from collision resistant hashes. So Synsomia works fine there. The other place where we use it, where we use Blake 2S in Sapling, is in the nullifier PRF. And that's what we replace with the construction I showed before, which is using both Poseidon and a fixed space scalar multiplication. So the combination of those is a PRF.
Awesome. And I think our last one, or 5-minute warning, what components do you anticipate looking at further over the next 2 years? Are there any stones left unturned?
I don't think there are. I mean, obviously, we're going to be thinking a lot over the next, well, we're already thinking about like ZSAs and stuff like that. So we've been incorporating the idea that ZSAs will be a thing someday into our development and design of Orchard to make sure that we leave room for that kind of stuff. So that's been on our mind. But in terms of like optimizations or things like that, just probably getting prototypes that work with recursion really efficiently, which might require changing the protocol a little bit, but not significantly, will probably be the next step. But yeah, that's pretty much it.
So one thing we could potentially do is replacing Samir with Poseidon if we ever became sufficiently confident in Poseidon to do that. We might use Poseidon anyway in the recursion construction for Fiat Shamir. Yeah, but we didn't want to use it. We didn't want to rely on it for the Merkle tree or for privacy in Orchard because it's just too new.
Awesome. I think we're at time. Thank you all for the awesome questions. Thank you, Sean and Dara, my co-presenters. We'll see you in the Discord.
Cool. See you. Thank you, everyone.
Bye.
Thank you.